peel back the metal, dive into the spinning heart of these machines, and reveal the science that makes flight possible. Buckle up. Let's explore the world of airplane engines. Let's rewind to the early 1900s, a time of incredible innovation and boundless dreams. People had dreamed of flight for centuries, imagining soaring through the skies like birds, a concept deeply rooted in mythology and human ambition. But the real challenge wasn't just defying gravity, it was creating sustained forward motion, a controlled and reliable way to propel oneself through the air. It wasn't just about lift, about getting off the ground momentarily. Gliders, for example, could soar briefly, catching the wind and gracefully gliding for short distances. But sustained, controlled flight needed a continuous push, a reliable source of power, an engine that could keep the aircraft moving forward against the forces of drag and gravity. Early engines, however, were far too heavy and cumbersome, rendering them impractical for flight. They lacked the necessary power-to-weight ratio, that is, until the Wright brothers came along. And their skilled mechanic, Charlie Taylor, played a crucial role in their success. Together, they built a lightweight, 12-horsepower engine from scratch, a remarkable feat of engineering ingenuity. This custom engine used controlled gasoline explosions within its cylinders. These explosions generated the power needed to spin propellers. The spinning propellers pushed air backward, creating thrust and propelling the plane forward, a direct application of Newton's third law of motion. On December 17, 1903, at Kitty Hawk, North Carolina, a location chosen for its consistent winds, their flyer, after numerous attempts, finally took off for a brief but momentous 12 seconds. This short flight was a monumental achievement, proving that sustained, powered flight was indeed possible. That tiny 12-horsepower engine was the ancestor of every airplane engine that has flown since, from piston engines to powerful jet turbines. The real breakthrough? Solving the critical power-to-weight problem, creating an engine strong enough to lift itself and the aircraft. It sparked the aviation revolution, igniting a period of rapid innovation and development in aircraft technology, ultimately making flight a reality for billions of people around the globe. The Wrights' innovation definitively showed that with the right engine design and the right amount of power, the sky was no longer the limit, but rather a vast and open highway. Every modern flight, every commercial airliner, every private jet, traces its lineage back to that first sputtering motor on the sands of Kitty Hawk. The journey from a humble bicycle shop in Dayton, Ohio to the boundless expanse of the sky irrevocably changed the world. It all started with a simple yet ingenious engine, meticulously crafted and tirelessly tested, and that's how, against all odds, we finally got off the ground and into the age of aviation. The story of flight is a relentless pursuit of innovation, and it all began with a spark of ingenuity. After the Wright brothers, engine tech soared, pushing the boundaries of what was thought possible. Piston engines ruled for decades, becoming the workhorse of the skies. They were the heart of legendary planes like the Spitfire, known for its agility and speed, and the Mustang, a long-range escort fighter that dominated the skies. These engines ignited fuel in a controlled explosion to push pistons, a marvel of mechanical engineering. The linear motion was then converted to rotational force, spinning propellers for thrust. It was a direct mechanical approach, elegant in its simplicity. And this technology is still used in small planes today, showcasing its enduring legacy. But as planes needed to reach for more speed and higher altitudes, a new challenge emerged. Piston engines, with their inherent limitations, began to hit their limits. Enter the turboprop, a hybrid solution that bridged the gap. It's essentially a jet engine that spins a propeller, combining the best of both worlds. This made it perfect for efficient short-haul flights, connecting communities with reliable air travel. Then came the turbojet, a revolutionary leap in aviation technology. This design featured no propeller, marking a significant departure from previous engines. Instead, it relied on just a high-speed blast of hot gas expelled from the rear. This created pure jet thrust, propelling aircraft to unprecedented speeds. Turbojets revolutionized air travel, shrinking the world and connecting continents. They were instrumental in making high, fast flight possible, opening up new horizons for exploration and commerce. Today's commercial king is the turbofan, an evolution of the turbojet. A massive front fan pulls in a huge volume of air, setting it apart from its predecessors. But here's the clever part. Most of that air bypasses the engine core. This design results in efficient, quiet thrust, making air travel more sustainable and comfortable. Only a fraction of the incoming air is actually burned within the engine's core. The rest accelerates out the back, creating a powerful propulsive force. This innovative approach boosts efficiency and significantly reduces noise pollution. Turbofans power everything in the modern aviation landscape, from jumbo jets carrying hundreds of passengers to modern airliners connecting the globe. Fighter jets, on the other hand, often use turbojets, or low-bypass turbofans, designed for raw speed and unmatched maneuverability. Some even incorporate afterburners for that extra surge of power when needed. Each engine type evolved to meet new challenges and specific demands, whether it's achieving incredible speed, maximizing fuel efficiency, or delivering sheer power. From the early days of pistons to the sophisticated technology of jets, it's all about matching the right engine to the mission at hand, optimizing performance for the task. The evolution continues, driven by the relentless pursuit of improvement. With each new design building upon the lessons learned from the last, pushing the boundaries of what's achievable. Propellers, jets, and fans, each represents a pivotal moment in aviation history. Each changed how we fly, shaping the world we live in today. And the story isn't over yet. The future of flight promises even more exciting innovations. Not all airplane engines are created equal. Their size and type depend on the plane's job. Small planes use compact piston engines about as powerful as a family car, perfect for low-speed, low-altitude flights. Turboprops bridge the gap, powering regional airliners with efficient, reliable engines for short hops. But for long-haul jets, it's all about the giant turbofan. The GE90, for example, is wider than a 737's fuselage and weighs 9 tons, built for non-stop intercontinental power. Fighter jets need slim, high-performance engines for speed and agility, often with afterburners for bursts of thrust. Every engine is tailored to its mission, small and efficient or massive and powerful. The right engine makes the right flight possible. From weekend flyers to globe-spanning giants, it's all about matching science to purpose. Engine design is a perfect fit for every flight. That's the beauty of aviation engineering. Let's break down the fascinating process of how a jet engine works. We'll explore the core principles that allow these incredible machines to generate thrust and propel aircraft through the sky. To understand it all, remember these 4 key words. They're the foundation of jet propulsion. Suck, squeeze, bang, blow. These 4 actions, happening in rapid succession, are what make flight possible. First, the giant front fan sucks in a massive amount of air. This is the initial stage of the process, drawing in the necessary oxygen for combustion. Interestingly, some of this air bypasses the core of the engine, but a significant portion enters the compressor section, the next critical stage. Inside the compressor, a series of rapidly spinning blades squeeze the air, dramatically increasing its pressure and temperature. Next, this highly compressed air enters the combustion chamber, the heart of the engine. Here, fuel is precisely injected through specialized nozzles and mixes with the compressed air, ready for ignition. And then, bang! The mixture ignites, creating a continuous, incredibly powerful burn. This controlled explosion generates a tremendous amount of energy. The resulting hot, high-pressure gas then rushes through the turbine section, spinning the turbine blades, which are connected to the compressor and fan via a central shaft, keeping the entire cycle going. Finally, the hot gas blasts out the back through the exhaust nozzle, blow, creating the powerful thrust that propels the plane forward at incredible speeds. This entire cycle happens thousands of times per minute, a testament to the engine's incredible efficiency and power. It's a continuous process, efficiently turning fuel into the forward motion that keeps us aloft. And remember, the bypassed air contributes to both increased fuel efficiency and quieter operation. It's truly a marvel of modern engineering, a complex system working in perfect harmony. All of this incredible activity is happening within that seemingly simple spinning engine. Suck, squeeze, bang, blow, simple words to describe an incredible source of power. That's the fundamental secret behind every jet flight you've ever taken. So, next time you find yourself flying, take a moment to appreciate the engineering marvel happening right there under the wing. That's jet engine magic, made real by the power of science and human ingenuity. The story of airplane engines is one of constant evolution. From the Wright's 12-horsepower motor, piston engines grew into supercharged monsters by World War II, pushing planes to their limits. The real leap came with the turbojet. No pistons, just turbines and pure jet thrust. Early jets were fast but inefficient and short-lived, paving the way for better designs. The Cold War drove rapid advances, more compressor stages, tougher alloys, and afterburners for military power. The high-bypass turbofan, invented in the 1960s, changed commercial aviation, quieter, more efficient, and able to fly farther. Today's engines use carbon fiber fans, computer-shaped parts, and single-crystal turbine blades that withstand extreme heat. Each generation is quieter, stronger, and more reliable. The journey from simple pistons to today's marvels is a testament to relentless innovation. And the evolution isn't slowing down. Modern turbofan engines do more than just push planes forward, they are complex systems. They generate electricity for everything on board: lights, navigation, entertainment, using generators spun by the engine core. The air you breathe at 35,000 feet, it's bled from the engine's compressor, cooled and piped into the cabin. Hydraulic systems that move massive control surfaces are powered by pumps driven by the engines. Engines are built with safety in mind. They contain broken blades, detect fires, and monitor thousands of data points every second. Redundancy and smart design keep flights safe and comfortable for everyone. Today's engines are self-monitoring, power-generating, air-supplying marvels. They're the heart of every modern aircraft. It's a symphony of science, all working together in harmony. Engines do much more than make thrust. They make flight possible. That's true engineering magic. The evolution of airplane engines is just getting started. Engineers are chasing greater efficiency and a smaller environmental footprint. Geared turbofans use gearboxes for quieter, more efficient operation. Open rotor engines, propeller-like but futuristic, promise big fuel savings, though noise and safety are challenges. Electrification is coming, small planes are going fully electric, while hybrids may power larger aircraft soon. Hybrid systems could use turbines as generators for distributed electric fans, revolutionizing design and cutting emissions. Sustainable aviation fuels, made from plants or waste, can power today's jets and slash carbon footprints. The future will blend efficient turbofans, new engine designs, electric systems, and cleaner fuels. Old ideas are being reinvented with new tech. The next leap in flight is already underway. The sky's the limit for innovation. The engines of tomorrow are being built today. From the Wright brothers' humble motor to today's intelligent turbofans, airplane engines are a triumph of science and curiosity. The next time you feel that push at takeoff, you'll know it's suck, squeeze, bang, blow in action. We've explored the history, compared engine types, and peeked into the future of flight. The story of airplane engines is still being written, and you're part of it. What fascinated you most? The Wright's ingenuity, the jet engine's dance, or the promise of electric flight? Let us know in the comments. Science grows with your questions and ideas. If you enjoyed this journey, like, subscribe, and share. Your curiosity fuels our next adventure. Until next time, keep looking up. Imagine waking up to an empty lot, a blank canvas of possibility, and then going to bed the very same night with a brand new, fully constructed house standing proudly there. A tangible dream realized in a single day. Back in 2018, Icon, a pioneering company in construction technology, turned this dream into reality. They used a giant 3D printer, a marvel of engineering, to build a 650-square-foot house in Austin, Texas. A modest yet fully functional home, showcasing the potential of this groundbreaking technology. And the truly astonishing part? It was completed in under 24 hours for less than $10,000. A fraction of the time and cost associated with traditional construction methods. This wasn't just a scaled-down model, a mere proof of concept or a prototype for demonstration purposes. This was a real, livable home, complete with all the essential amenities, including fully functional plumbing and electrical wiring, a testament to the practicality of 3D printed construction. That moment shattered the long-held idea, the preconceived notion, that 3D printing was solely limited to creating plastic toys and trinkets. Now, the focus has shifted dramatically. It's about scalability, the ability to produce on a large scale, speed of construction, and overall efficiency in resource utilization. Building directly from a precise digital blueprint, eliminating the need for manual interpretation and reducing errors. This process requires no traditional molds or complex assembly lines and generates almost no waste, contributing to a more sustainable construction industry. Think about the implications for disaster relief efforts. In the immediate aftermath of a devastating hurricane, you could potentially print durable and safe emergency shelters in a single day, providing rapid assistance to those in need. Or consider the possibilities for addressing the global affordable housing crisis. 3D printing offers a pathway to rapid, cost-effective construction of durable homes, making homeownership more accessible to a wider population. The very same core technology that allows you to print a customized phone case can be scaled up exponentially to print an entire house layer by layer with remarkable precision. In this exploration, we're going to break down exactly how this revolutionary process works, examining the different types of printers currently being utilized, and showcasing some of the incredible structures that are already being built around the world. If we can achieve the feat of printing a complete house in a single day, then the real pressing question that we need to address is, just how profoundly and rapidly will 3D printing technology reshape our world and change everything we know about construction and beyond? Let's dive in and explore the fascinating world of 3D printed construction. Have you ever wondered how a 3D printer can conjure a tangible object from the ethereal realm of a computer file? It seems like something out of science fiction, but it's a very real and increasingly accessible technology. The journey begins with a digital model, meticulously crafted using CAD, computer-aided design software. These powerful programs allow designers to sculpt and refine their ideas in a virtual space. Alternatively, you can explore vast online libraries and marketplaces where a universe of pre-designed 3D models awaits, ready to be downloaded and brought to life. This digital file is more than just a pretty picture. It holds every minute detail of the object, its precise shape, overall size, and internal structure. It's a complete blueprint for the printer to follow. Next, specialized slicing software takes center stage. It cleverly dissects the 3D model into hundreds or even thousands of incredibly thin layers, like the pages of a book. This software then translates these layers into G-code, a precise set of instructions that the printer can understand and execute. The 3D printer diligently reads the G-code and embarks on the construction process, building the object layer upon layer, in a process known as additive manufacturing. This is commonly achieved by melting plastic filament and carefully extruding it through a precision nozzle. Each newly deposited layer meticulously fuses to the one below, slowly but surely stacking up, transforming into the desired 3D object. The printing process can span anywhere from a few minutes to several days, largely dependent on the object's size and the complexity of its design. Once the printing is complete, you might need to carefully remove some support structures that help during the build, but generally, that's all there is to it. And just like that, you've successfully transformed a digital concept into a tangible physical reality. It's a form of digital magic, where creation happens one layer at a time, revealing the wonder of 3D printing. That encapsulates the core essence of 3D printing technology. Now let's delve deeper and explore the main types of 3D printers available today. There's more than one way to 3D print. FDM is the most common melting plastic filament and building objects layer by layer. It's affordable and great for prototypes or functional parts. SLA uses liquid resin and a UV laser for ultra-detailed smooth prints perfect for jewelry, dental models, and miniatures. SLS works with powdered materials, fusing them with a laser. It's ideal for complex interlocking parts and doesn't need support structures. DMLS takes SLS to the next level, printing with metal powders for aerospace, medical, and industrial parts. Each method opens new possibilities, from home gadgets to rocket engines. The right printer depends on what you want to create. Let's see what people are building right now. 3D printing is transforming industries. In medicine, doctors use printed models to plan surgeries and create custom prosthetics tailored to each patient. Engineers can design, print, and test prototypes in a single day, speeding up innovation. Even food is being printed. Custom chocolates, soft meals for patients, and plant-based meats with realistic textures. Manufacturers print custom tools and parts on demand, while small businesses create niche products without huge upfront costs. From replacement car parts to architectural models and even entire houses, 3D printing is everywhere. It's not just a hobby, it's a revolution in how we make things, and it's only getting bigger. But how is it changing manufacturing itself? 3D printing is shifting manufacturing from massive factories to local, on-demand production. Traditionally, making one item was expensive. Factories relied on mass production and global supply chains. With 3D printing making 1 or 100 costs about the same. Need a spare part? Download the file and print it locally. No warehouses, no shipping delays. This digital inventory model makes supply chains faster, cheaper, and greener. It also enables true customization products tailored to each customer, like custom-fit earbuds or eyeglass frames. Anyone with a good idea and a printer can launch a business from their garage. The future factory might be a network of millions of printers worldwide. Manufacturing is becoming democratized. So what's next for 3D printing? The future of 3D printing is poised for remarkable advancements. We're on the cusp of a new era where speed is paramount, transforming how we approach manufacturing and production processes. Innovations in new materials are set to revolutionize the industry, and smarter machines will drive efficiency and precision to unprecedented levels. Next-gen printers like CLIP, which stands for Continuous Liquid Interface Production, can now print objects in mere minutes, a stark contrast to the hours it used to take. This leap in speed is a game-changer. Soon we'll be able to print with a range of exotic materials, seamlessly mixing hard and soft elements within a single print, or even embedding electronics directly into products during the printing process, opening up new possibilities for smart devices and integrated systems. And the concept of four-dimensional printing is rapidly becoming a reality, envisioning objects that dynamically change shape when exposed to stimuli like heat, water, or even light. Artificial intelligence will play a crucial role, designing complex and incredibly efficient structures, and meticulously monitor prints in real time, ensuring quality and precision every step of the way, significantly reducing errors and minimizing waste in the production cycle. The field of bioprinting is also advancing at an astonishing pace. Scientists are now capable of printing functional tissues, intricate blood vessels, and are even diligently working toward the creation of fully functional organs for transplant. Looking beyond our planet, in space, astronauts will soon be able to print essential tools and replacement parts on demand, utilizing locally sourced materials found on other celestial bodies, ultimately making sustained off-world living a tangible possibility. 3D printing isn't just about the simple act of making things, it's about pushing the boundaries of what's achievable and making the seemingly impossible possible. The next wave of innovation will blur the line even further, increasingly blurring the lines between the realms of science fiction and tangible reality. In this exciting future, the only true limit is the scope of our own imagination. So, with all these incredible possibilities on the horizon, what do you think the future holds? We've explored how 3D printing works, the tech behind it, and its impact on everything from medicine to manufacturing. This isn't a passing trend, it's a foundational shift in how we create. The technology is getting faster, cheaper, and more accessible every day. What excites you most? Custom products, medical breakthroughs, or space exploration? Have you tried 3D printing? What did you make? Drop a comment below and share your thoughts or questions. Your ideas help shape the future of this technology. Let's keep the conversation going. Peace.
Imagine a mountain, silent for centuries, a sentinel of stone and earth. It stands as a testament to time, its peak often shrouded in mist, its slopes alive with forests teeming with life, a vibrant ecosystem thriving in seeming tranquility, and rivers carving paths through the landscape, nourishing the land with their cool, clear waters. People have lived in its shadow for generations, building their homes and lives in the fertile valleys below, never suspecting the power beneath their feet, the immense, slumbering energy that lies dormant, waiting. But deep below, pressure builds, molten rock churns, a subterranean ocean of fire and fury, a force ready to reshape the world, a geological titan stirring from its age-long sleep. The ground trembles, a subtle warning, an almost imperceptible vibration. Animals sense it first, their instincts honed by millennia of survival, fleeing to higher ground. A wisp of steam escapes the summit, a ghostly plume against the azure sky, a sign of the awakening. The sleeping giant is waking, stretching its limbs of fire and stone, preparing to unleash its might. Suddenly the mountain erupts, a cataclysmic explosion, a rupture in the Earth's crust. Ash, a suffocating blanket that blots out the sun, a rain of gritty particles. Gas, poisonous fumes that choke the air, a toxic breath from the Earth's core. And rock explodes skyward, projectiles of destruction hurled into the atmosphere. In a deafening roar, a sonic boom that shatters the silence, a primal scream of the planet. This is the planet breathing fire, its molten heart exposed, a raw display of geological power, a force that can build islands, creating new land masses from the depths of the ocean, or erase civilizations, burying entire cities under layers of ash and lava, a stark reminder of nature's dominance. The peaceful landscape becomes chaos, a scene of devastation and destruction, transformed in an instant. molten rock lighting the sky, an infernal glow illuminating the night, a spectacle of terrifying beauty. We're witnessing a fundamental process of planetary evolution, the very forces that shaped our world, a volcano erupting, a reminder of the power that lies beneath our feet. But this isn't random. There is order in this chaos, a pattern to this seemingly destructive event. It's governed by the same laws that shape the stars, the universal principles that dictate the cosmos. To understand volcanoes, to decipher their secrets, we must delve deeper. We must journey downward, into the heart of the planet, into the fiery depths, into Earth's interior, exploring the layers of rock and magma that lie beneath the surface, and back through time, tracing the history of volcanic activity across millennia. We become detectives, piecing together the puzzle of the Earth's fiery past, piecing together from lava flows, analyzing the solidified remnants of past eruptions, and seismic waves, interpreting the vibrations that ripple through the Earth. So, come with me. Let's embark on this journey of discovery together. Let's explore the science, the intricate mechanisms behind these magnificent forces of nature, and the profound impact they have on our planet. What secrets do volcanoes hold? What can they tell us about the Earth's past and future? The ground beneath us is alive, pulsating with energy, a dynamic and ever-changing landscape. And it's ready to tell its story, a story written in fire and stone, a tale of creation and destruction. A volcano isn't far more complex than that. It's not simply a peak rising above the landscape. It's a rupture, a vulnerable point, in the planet's otherwise solid crust, a place where the Earth's internal forces find a release. It's a vent, an opening, where molten rock, superheated and under immense pressure, ash, and a cocktail of noxious gases escape from the fiery depths, from deep within the Earth. The iconic cone shape, that classic image of a volcano, is built slowly, painstakingly, by countless eruptions over vast stretches of time. Layer by layer, each eruption adding to the growing structure. Volcanoes tend to cluster along the edges of tectonic plates, along those dynamic tectonic plate boundaries, where Earth's crust is constantly under stress, cracking and shifting in response to immense forces. But sometimes, defying expectations, they form far from these boundaries. In the seemingly stable middle of plates, in places like Hawaii, a volcanic paradise over hotspots, those mysterious plumes of intense heat, plumes of superheated rock rising from deep within the mantle, punching through the crust, relentlessly pushing upwards. As plates slowly drift across the globe, these hotspots leave behind trails of volcanic activity, creating chains of volcanoes, each island and seamount telling a story of Earth's restless interior and its geological history. Every volcano, regardless of its size or shape, from the perfectly symmetrical cone of Mount Fuji to the sprawling shield volcano of Mauna Loa, is a window, a direct connection into our planet's dynamic and ever-changing heart. They serve as a constant reminder that Earth is not a static, unchanging rock, but a living, breathing planet, constantly reshaping itself through volcanic activity and other geological processes. Even the very air we breathe and the vast oceans that cover our planet owe their existence, at least in part, to the gases released during ancient volcanic eruptions billions of years ago. Volcanoes are not just mountains rising above the horizon. They're the architects, the builders, the sculptors of our world, constantly shaping and reshaping the landscape around us. To truly understand the awesome power of volcanic eruptions and the forces that shape our planet, we must embark on a journey deep inside the Earth, peeling back the layers to reveal its inner workings. Our planet is meticulously layered, starting with a solid core, a sphere of intensely hot, dense metal, surrounded by a liquid outer core, a swirling ocean of molten iron, and then a vast mantle composed of hot, slowly moving rock, extending thousands of kilometers. Heat, largely generated from radioactive decay, drives powerful convection currents within the mantle, like a giant engine churning beneath our feet. It is here, deep within the mantle, that magma is born. Molten rock formed in specific zones where the temperature and pressure conditions are just right for melting, particularly at plate boundaries, those dynamic zones where Earth's tectonic plates interact. Pressure drops significantly, or the presence of water dramatically lowers the melting points of rocks, creating vast quantities of magma. Magma, being less dense and lighter than the surrounding solid rock, begins to rise slowly, making its way upwards and eventually collecting in large underground chambers. These magma chambers can simmer and evolve for thousands, even hundreds of thousands of years, behaving like immense pressure cookers deep beneath the surface. Inside these chambers, magma is not a uniform liquid, but rather a complex mix of molten minerals, dissolved gases, and suspended crystals. Sometimes, under the right conditions, the magma cools and solidifies underground, slowly forming granite and other intrusive igneous rocks. Other times, a fresh injection of new magma into the chamber raises the overall pressure. As the magma cools, dissolved gases begin to separate and build up, increasing the internal pressure, effectively priming the volcano for a potential eruption. The stage is now set for a dramatic and potentially explosive release of energy. The volcanic engine is primed and ready to unleash its power. The magma chamber is under immense pressure. When the rock above fractures, magma surges upward through cracks. As it rises, pressure drops. Dissolved gases rapidly expand, like a shaken soda. This expansion drives explosive eruptions, propelling magma skyward. The process accelerates, more bubbles, faster ascent, more power. Lava bursts through vents, shattering rock and launching debris miles high. The volcano becomes a cannon, gases the gunpowder. Whether the eruption is gentle or catastrophic depends on magma's thickness and gas content. What kind of show will this volcano put on? Not all eruptions are alike. Effusive eruptions, like those in Hawaii, produce rivers of fluid lava. Spectacular, but relatively gentle. Explosive eruptions, fueled by thick, gas-rich magma, unleash ash clouds and pyroclastic flows, devastating everything in their path. Mount St. Helens in 1980 was a classic explosive eruption. Plinian eruptions can blast ash 20 miles high, affecting global climate. The deadliest product is the pyroclastic flow, a superheated avalanche impossible to outrun. Between these extremes are Strombolian and Vulcanian eruptions, each with unique bursts and blasts. A volcano's style depends on its underground chemistry, magma's composition, temperature, and gas. The type of volcano near you reveals the geology beneath your feet. Each eruption tells a story of Earth's inner workings. History is shaped by great eruptions. Mount Vesuvius buried Pompeii in ash, preserving a moment in time. Krakatoa's 1883 eruption was heard 3,000 miles away, triggered tsunamis, and cooled the planet. Mount St. Helens erupted sideways, flattening forests and revolutionizing volcanic science. These events remind us a single volcano can change the world. Supervolcanoes, like Yellowstone, have unleashed eruptions thousands of larger, capable of plunging Earth into volcanic winter. While rare, their potential impact is immense. Volcanoes have shaped landscapes, climates, and civilizations. Their power is a reminder of Earth's restless energy, and their story is far from over. How do we predict eruptions? Volcanologists monitor volcanoes' vital signs: earthquakes, ground swelling, and escaping gases. Seismometers detect tremors as magma moves. GPS and satellites measure ground deformation, tiny bulges that signal rising magma. Scientists analyze volcanic gases for clues about what's happening below. By combining these signals, they build a picture of the volcano's plumbing. This allows for warnings and evacuations, saving lives. The work is dangerous, but vital. Volcanologists are our early warning system against Earth's fury. Their discoveries help us understand and live with these powerful forces. What mysteries will science uncover next?
Ever wondered how a humble sausage, a staple in cultures around the world, became such a culinary icon? From breakfast tables to gourmet restaurants, the sausage holds a special place. It's more than just meat in a tube. It's a story of survival, ingenuity, and a surprising amount of science. It represents a time when resourcefulness was key. Sausage is one of humanity's oldest processed foods, predating many modern culinary techniques. It was born from the fundamental need to preserve every precious scrap of meat, especially before the advent of refrigeration. Nothing could be wasted. Salt and smoke weren't just flavor enhancers, they were lifesavers, transforming leftover cuts into something lasting, safe, and surprisingly delicious. At its core, sausage is a simple yet elegant blend of ground meat and fat, a combination that, when executed correctly, creates magic. Get the ratio just right, and you have juicy, flavorful perfection that bursts with every bite. But get it wrong and you're left with a dry, crumbly disappointment, something akin to sawdust. The casing, traditionally made from animal intestines but now often utilizing modern alternatives, plays a crucial role. It isn't just a wrapper, it actively shapes the sausage's texture, contributes to its overall flavor profile, and provides that signature satisfying snap we all crave. So, are you ready to delve into the fascinating world of sausage making and see what really goes into crafting a truly great sausage? We'll break down the underlying science, explore the crucial choices involved, and demonstrate the hands-on techniques that transform simple, humble ingredients into something truly extraordinary. So, grab your apron, because this is far more than just a simple recipe. It's a comprehensive journey into the very heart of food science and culinary artistry. Let's get started and unlock the secrets of the sausage. The first step in crafting exceptional sausage: choosing your meat. It's the foundation upon which all other flavors and textures will be built. Take your time, consider your options, and select with intention. Pork shoulder is a classic choice, and for good reason. It offers a perfect balance of lean meat and rich fat, creating a juicy and flavorful sausage. Aim for a ratio of about 70 to 80% lean meat to 20 to 30% fat. This ensures a moist and delicious final product, preventing the sausage from drying out during cooking. While pork is traditional, don't be afraid to experiment. You can use beef, offering a bolder, richer flavor profile. Chicken, with its delicate taste, can create a lighter sausage, or even venison,